Hello everyone, my name is Babak. I would like to welcome you to the second session of Air Conditioning and Ventilation webinar from SimScale. I will have a short introduction of myself later. We already had the first session on CFD flow in a data center, and today we also have prepared a very nice case for you. We will in details demonstrate how small changes in your design could lead to considerable differences in the results of your simulation, and how these changes in the result could help you make informed decisions on how the final product should look like. So, about myself, I am a senior fluid dynamics engineer at SimScale. My background is in both computational and mechanical engineering with an emphasis on fluid dynamics. So I have both experience in compressible and incompressible flows. Of course, it's a vast area, so there were certain applications that I have more experience with. I also have done quite some work on heat transfer applications, again in different areas, also on mesh-free methods. At the same time, more on the computational side, I have experience on technical computing. Maybe I could divide that into different areas, but what is very closely related to the work that I did are more high-performance computing, so HPC, also method development, solver development, maybe analysis of the errors. So these are the areas that I have done work with. So I also would be very happy to discuss these topics, those that are related to this webinar, in the course of this webinar, and those that are not, maybe in the forum or by other means. So with that introduction, let's have a look at today's agenda, see what we're going to talk about. So this second session focuses on smoke propagation in a parking garage. First, I will start with a very brief introduction about CFD and SimScale. Parts of this are covered in the previous session as well, so I will not go through details there. Just very quickly for those who have joined us from this session, but in case you're interested to hear more, we have uploaded the videos of the first session both in our forum and in our YouTube channel. I encourage you to have a look at those. Then I explained the problem, how CFD is going to help in our analysis of smoke propagation. I will tell you some details how to simulate this problem specifically with SimScale. So first I will cover the generics of the problem and then some specifics about our platform. We will have a live demo, so I will show you how to set up the mesh and how to set up the simulation. Specifically, since we are going to use some of the features of the meshing that we normally do not use them on the automatic settings, this also would be interesting, so I will spend some time there, and then of course I will move forward to setting up the simulation. Once that is done, I will show you the results. We will have some discussions on the results to show how minor changes that we've done to each case results in completely different results. After that, we will have the homework. So we've prepared a case for you. Once we cover the material in the webinar, you could start with that homework. We also have prepared a nice step-by-step tutorial on how to set that case up. At the end of this session, I will show you how to access that project, and I'll show you this step-by-step tutorial in the forum. At the end, we will have questions, so I will encourage you to mark your questions, maybe note them down or add them to the questions in the course of the webinar, and I will address them at the end. So our company started in 2010 as a consultancy, but our platform, the SimScale platform, started being developed from 2011. So we're based in Munich, where actually I'm broadcasting this webinar from. Our team has grown quite rapidly recently. We have about maybe 40 people from different parts of the world with different backgrounds. And also our customers are really from all parts of the world. We have customers from more than 190 countries. This is just not a very diverse geographical distribution. Also in terms of the industries that are involved, in terms of the specialties of our customers, we really cover many different industry verticals. For those who don't have too much experience with CFD, maybe with the process of simulation specifically for the case of this webinar with CFD. This is the traditional design process. So you start with, there's a need, so you start with a design. And you take that design and you have to develop some sort of physical prototype of that design. Once that is done, you start with testing. Based on the result of testing, you go with some modifications in your design. Normally this process, these steps from 2 to 5 have to be repeated several times until the final product satisfies the kind of requirements we have. Then the manufacturing could start. And the new trend, the new way of doing it is to use simulation to kind of compress the steps, the second step to the fifth step into 2 steps. So to be specific, physical prototype development and testing are going to be compressed inside simulation. It's easier, it's much faster, it's absolutely cheaper in terms of the costs of designing and testing a prototype. So the overall idea is to save both time and money by adapting this new workflow. And this is actually what we intend to do here. So there are other solutions to address this, to use simulation, to use CFD, to develop a product. But we at SimScale address this problem from 3 different angles. So from the traditional way of doing this, from traditional way of using simulation in your process, there are 3 aspects that are normally very difficult to solve. One is being accessible. So we require no hardware, no software. You just need to log into your SimScale account in your browser, and you have suddenly access to virtually unlimited computing power, simulation software, different types of simulations. So all of this is placed at one platform in your browser. You don't need to worry about anything else. So this is the first aspect that our platform addresses. Second is the cost. Traditionally, the solutions that offer this kind of simulation capability are very, very expensive. They are designed with a lot of features, with a lot of capabilities, but at the same time they're very expensive. So it's not just about the cost of the software itself, it's also the cost of providing the infrastructure. If you have larger cases, of course, it means that this is some extra cost. So overall, the aspect of the investment that you have to put in to be able to get something meaningful out of your simulation is quite high. In that, we offer all of our features of the platform for free for all of our users. So as long as you make the content that you produce available in our community, make it publicly available for everyone, you can use all of the features that are provided. There's no limitation on the number of the features, on the capabilities. There's virtually no limitation when you want to make the content that you create public. And the last aspect is we really intend to have this for everyone. So generally, this kind of software is very difficult to learn. So it is designed for specialists. It is designed for people with a lot of experience. And we tend to solve this problem by having a crowdsourced know-how. we already have more than 50,000 different types of projects. So if you go into our public library and try to find the kind of application you have in mind, it's very likely that you find something very close or something that gives you a very good idea of how to tackle that problem. So these are the three aspects that we specifically with our platform have addressed, and hopefully it's going to extend even further in future. And as I mentioned, it's not just about it's CFD. We also have solid mechanics analysis. We have particle flow. And in CFD, we have different types of analysis. We have incompressible and compressible flows. We have heat transfer, multi-phase flows. I think for those who have used our platform, they've seen all of these types maybe through using the projects that others have provided, or maybe even doing the simulations yourself. And it's not just about the analysis types. We also provide some advanced functionality independent of the type of the simulation that you're interested in. For example, using particles, using bodies that have certain degrees of freedom to move relative to the domain. Specific application for machinery that use rotation and the specific forces that need to be taken into account in those cases. So all of these cases are really supported in our platform. Okay, so with this introduction, I hope it was not too long for those who have attended the previous session. We move forward to the specifics of this session of the webinar. So as I mentioned, we are addressing smoke propagation in this session. So let's see how smoke propagation is relevant to the theme of the current webinar series. So as I said, you could address this problem from two aspects. One is safety and one is the quality. So we will see how safety and quality could be addressed in the two simulations that I'm going to present. So let's consider the case of a parking garage. So we normally are dealing with large spaces, closed spaces that have several factors that could be risky in terms of the quality of the air and also the safety. So let's assume if something goes wrong, if one of the components, one of the electronic components catches on fire, there should be already the design of the parking garage should be in a way to be able to handle this situation very easily. So the smoke, the heat should be removed from this closed space. Also, some certain areas must be provided for the cars, for the people who are inside the garage to actually leave this space, go to the safety. And at the same time, since we have many sources that generate the smoke, actually the cars inside the garage, generally the quality of the air in terms of the percentage of the smoke is also very important. So in this way, we could address this problem in a few specific bullet points. So first would be the improved quality of the air in the indoor space. For the people who leave their car, they walk from their car to the outdoor space, or those who want to go to their car and start their car, they normally spend at least a few minutes inside this space. So the quality of the air for them should at least have some minimums. Second is the cases of emergency. When something goes wrong, when there's a case of fire, when maybe some equipment actually are overheating and they catch on fire, so we have to remove the extra smoke from the system. This also is one of the cases that need to be considered. Also, when such an emergency case happens, in the meantime that it is ongoing, it has to be we have to provide certain places, certain areas that are safe for the people who are inside the garage. So, for example, certain pathways that they can use to evacuate the garage, or certain areas that are safer in terms of the smoke and heat that they could actually gather in. And the final point would be being able to satisfy the kind of regulations and standards that building such spaces requires. So normally there are certain standards that year by year they become more and more strict that need to be met before such a facility could be used publicly. And let's see how CFD can address these points that I mentioned. So the first point would simply be simulating how effective the ventilation system in such a space is. See how the removal of the normal amount of smoke that is generated inside a garage is. Second is seeing how the distribution is. Does the normal amount of smoke normally goes to a certain corner, certain part of our garage, or does it distribute uniformly? And how we can, based on this understanding, how we can design the vents to remove this smoke. At the same time, we could see in case something happens, in case there's a fire, how the front of the fire, how the smoke propagates inside our domain. How long does it take for it to reach all parts of the garage? How long it takes for it to reach some risky levels that after that nobody should be inside the garage? All of this could be addressed by CFD. And at the same time, we could very quickly test a lot of what-if situations, meaning that we're going to actually cover this very nicely, meaning that what if I add an outlet somewhere? What if I increase the mass flow of this inlet to a certain number? This also would be something that is very easily addressed by CFD. So with this, let's have a look at this specific problem that we have. So as I said, we're going to address a parking garage. Here on the left, you can see the geometry that we have. So it's a closed space. We have certain columns, which is very typical of such spaces. We have a number of ventilation ducts. They could be used as inlets or outlets. We actually use different combinations of them for the demonstration. And for the case of emergency, we also have created a source to simply put some smoke into our domain. It could be, for example, an electric unit. It could be anything. So this is the general case that we're going to address. And to simulate the cases that I mentioned, we have created two scenarios. So the first scenario is the propagation of smoke inside the parking space. We are actually interested in two cases. One is a transient analysis of this case, meaning that we are interested in knowing the instantaneous spread and concentration of the smoke. And one is the steady state analysis of this case, meaning that once something, for example, a case of a fire or excessive generation of smoke by some unit, once this happens, how is going to be the distribution of smoke and heat in the long run? How is it going to settle down in the end? What happens after, for example, an hour or two after the generation of the heat has started? So these two would be covered in our first scenario. And in our second scenario, we study the clearance of smoke. So this is here. We don't have we do not have an emergency. We have a normal case where different sources, for example, cars, generate some smoke, and then these the aim of this scenario is to see how quickly we can remove this smoke from the system. Specifically, how the distribution of our inlets and outlets affects the final distribution of the smoke, starting from an initial state. So this would be what we will do in the second scenario. So for the first scenario, as I said, we're going to be interested in two cases. So case one is what you will see here. We have a smoke inlet. You can see it here on the left. We have one outlet at the far end of our of our garage, and we have an air inlet which is placed kind of in the middle of the two. This would be case 1 from scenario 1, and we have a case 2 from scenario 1, which is essentially the same thing. We simply rearrange and change the number of inlets and outlets. So the smoke inlet stays the same, but we use an air inlet at the far end of our garage, and we add 2 outlets in the middle. So we also could call this active management. This is a case that you design a system to behave differently based on what the input is. It means that maybe when there's no emergency, you don't need to have 2 outlets. You only need to have 1 inlet and 1 outlet. You could save a lot of energy. This reduces the complexity of the system. But in case something happens, in this case, when we have this smoke inlet, you want to change the functionality of the system in order to be able to handle this emergency case fast and safe. So these 2 would be covered in scenario 1. And in the scenario 2, we initially are going to fill up our domain, our complete garage, with smoke. We add a concentration of 0.5. This kind of reflects what is the ratio between the clean air and the smoke. 0.5 is kind of an indicator of this ratio. So we're initially going to fill up our garage with this 0.5 concentration of smoke, and then we use 2 outlets and 2 inlets to see how the smoke is being removed. To see how the arrangement of these inlets and outlets actually facilitate this removal of this smoke from our system. In this, as you see, we kind of flip the position of the inlets. So in the first case, we have 2 outlets, 1 at the far end, 1 opposite of it, and in between we have 2 inlets. And for the second case, we simply change the position of these inlets and outlets to see how this affects the overall distribution of the smoke in our system. So now that we are you're familiar with this case, with the definition of the cases that we're going to do, I will also very quickly show what kind of parameters we have to use to do this simulation, and then I'll move to our platform to actually do a demonstration of the setup of the simulation. So what we will do on the platform is to show how the cat upload works. You've done something very similar before in our first session. We again used importing a cat directly from Onshape into our platform for this step. Then meshing and simulation. I will show how the meshing works in more details this time, because we specifically are interested in adding some certain refinements on parts of our domain. This would be the second step, and finally we analyze the results to see what kind of design decisions must be made. For that, I will come back to my slides and show how the results look like, and based on that, how we can make design decisions. So yeah, as I said, we will use our integrated importing of geometries from Onshape. As you can see here, this is already covered before, so I will not go through details there, but maybe a few words on the setup of the simulation. So we are going to use a hex dominant parametric mesh generation. It means that we are going to define all of the parameters. We are going to use all of the control that we have over our mesh in terms of what kind of refinements do we have, how refined or how coarse a part of the domain must be. If you're specifically interested in more details, more accuracy in specific parts of our domain, this is how we define them. So it would be interesting to see how these refinements actually are defined and how they work. We use a scalar transport with turbulent modeling. For our passive scalars, we actually use smoke. So smoke itself is physically, it's just
very small particles that are moving in air. So this is what actually smoke itself is. So in this case, since the size of these particles are very small, they kind of move simply with air. So they do not affect the movement of the air itself, but they move with the air. And that is why we can use this passive scalar analysis type. This is not always the case. So if you have larger particles or if different physics is actually governing our system, it's not always valid to use passive scalars. So one has to make this decision very carefully, but in this case, it's a very good and valid assumption. So we have to define two parameters that kind of define how these particles, how these solid smoke particles inside air move around. These two are, one of them is the turbulence Schmidt number, the first parameter here, and the second one is diffusivity. So this turbulence Schmidt number, we normally have a range close to 0.7 to 0.75. So unless you know that you have to use a different parameter, just use the one that we've provided here or we have by default on the platform. This parameter kind of is a representative of how the momentum is diffused in our system over how the mass is diffused in our system. This is what this parameter physically means. And the second one is mass diffusivity, which means that how, because of the small motion of fluid elements, how a mass is gradually being diffused in our system. This second parameter physically represents this kind of motion. So in terms of time dependency, we will have 3 transient cases and 2 steady state cases. I will show all of them. Also, we will study the results in the end. For the choice of turbulence modeling, we use K omega SST. The advantage of using this model is that it brings the advantages of both K omega and K epsilon together. So we normally are interested in using K omega close to walls, but when we move towards the bulk in the middle of our domain, K epsilon is a better turbulence model. So what K omega SST does is it essentially creates a mix of these two methods and uses each of them in the relevant part of the domain. We use an inlet velocity of 0.35 meters per second. This is kind of a characteristic velocity of, it may be a realistic case when an emergency happens. We also use a duct inlet velocity, something between 0.1 to 0.15. This is also a characteristic of normal vent velocities in geometries like a parking garage. And let's see what we will look at for the output of our simulation. First, we will look at the 3D patterns of the air and also pressure distribution in the domain. It would be interesting to see what kind of velocities are we dealing with, also how the distribution of the pressure is. The next item, which would be very interesting, is the instantaneous scalar distribution in the domain. We want to see at each time where the front of the smoke is, specifically in case of the smoke propagation, and what the density of that front is, what the concentration of that front is. Later, we look at the time averaged distribution of the scalars. So in the long run, after half an hour, after 1 hour, how is the distribution of the smoke? And finally, to have some measures to make decisions based on, we will look at average flow rates and scalar values to kind of characterize each distribution, each setup, maybe distribution of inlets and outlets with 1 or 2 numbers and use those to decide whether the setup is what we wanted or whether we should make adjustments to it. So now let's move to the platform. Here I have the project open. So as you see, smoke propagation in a parking garage. this is the project overview page. We've prepared this for the second session of this webinar. I think you're familiar with what this page shows. We normally, at the bottom you see we have two different geometries. We have a number of meshes that you can see here. We will have a look at them inside the project. So I'll just go ahead and open the project here. Okay. First I will start with the mesh. Before that, I will just quickly remind you again how these geometries, the two that use in this simulation, are imported. You can either use this button here to upload from your own computer, or you can use this one and import from Onshape. I will not do that again since this is already done, but the details of this are covered in our first session, so I encourage you to have a look at the videos that are uploaded there to see how this exactly is done. So here is our geometry. Maybe I'll hide the outer faces so you can see what is happening inside the garage. So as you see, these are the columns that I mentioned. Here we have the source of the smoke, and here we have 3 vents. In different setups we use them differently. Sometimes they're inlets, sometimes outlets. I think in one of the cases we don't use this one here to kind of study the number of inlets and outlets that are used. So this is the geometry. I think since we covered how it looked and what kind of a specification it is going to have, I will not discuss it further here. Let's have a look at the mesh. So I will take you first to setting up of a mesh. As I said, we're going to use a hex dominant parametric meshing operation. So in this case, when you want to use this this meshing operation, you have complete freedom. As you can see in the middle, you have complete freedom over the choice of the parameters. So if you know what you're doing, of course, go ahead and change these parameters. Otherwise, we normally tweak these parameters to fit the kind of application you have. There are 2 or 3 things that I will show them now that are more important. It would be nice to check them. But other than that, we could simply skip these parameters and go to define mesh refinements here on the left. So the first one is the mesh base. So this is a box. Let me show it here. So you see this is like a rectangular box that covers all of our geometry. So this kind of defines how the base mesh is going to look like. Based on the dimensions of this box, a base mesh is created, and then based on the features of our geometry, we're going to have refinements. We're going to have a mesh that really represents the features of the geometry. So in order to have this, if you simply use your mesh, use your geometry from here and click here on new mesh, we automatically create this box and fit it to your geometry. So you don't need to set the values here. Of course, if you're interested in increasing the size of this box, or for example, when you're doing some external aerodynamics, you want to take a larger box, you can use that. Otherwise, you can rely on the default value that we calculate from your geometry. So this one was the first one. Then there's a material point that kind of distinguishes the inside and outside of your geometry. This is again a value that we create. If you are if you want to be sure, you can simply visualize it and see if it falls inside your geometry. You see it is placed here. I hope you can see it in the GoToWebinar, and it kind of distinguishes the inside and outside of a geometry. These 2 plus 1 more setting are the most important things in defining a hex dominant parametric mesh. So this is the third one, the number of the meshes in each direction in the bounding box. So that base mesh box that I showed you initially is going to be populated by this many cells in each direction, 85 in X, 70 in Y, 10 in Z. Again, if you create this operation, we assume a medium mesh size, and based on that, we calculate these values for you. Based on your specific application, you could be interested in decreasing or increasing these. But again, we provide values that fit the kind of application you want. So if you have requirements on top of that, go ahead and change these as well. For the projected number of the cells that our mesh is going to have, we decide that 4 cores are enough. So this would be enough for this, this set of settings. And then I'll move down here to add a mesh refinement. You simply can click on New here, and it brings you to a menu like this. So for this case, we added 4 different types of refinement. So refinements are certain ways to tell the meshing algorithm to make the size of the mesh finer or coarser at certain places. For this case, we used a surface refinement. We assigned it to solid. If you see, solid is basically all of our geometry. So by this, we are telling the measure that I want to make sure all of the faces of my geometry have 2 levels of refinement. The second refinement that we use here is a surface refinement, but this time to a 3rd level. So 1 level more than what we had before. If you see which faces this one is assigned to, you can see in this case it's assigned to these 2 inlets and outlets. Because here the flow has more features, we want to make sure the features of our mesh is fine enough to be able to capture, the gradients of velocity, for example, or changes in the concentration close to those areas. Also add a region refinement. A region refinement, if you see what it is applied to, it again creates a geometrical shape, in this case a Cartesian box, says that whatever cell that falls inside this Cartesian box should be refined 1 level, as you can see here. So this kind of guarantees a minimum quality of the cells all over our domain. In the end, I add a feature edge refinement. The feature refinement looks at the features of the geometry. If we have curvatures, if we have edges, if you have faces, maybe corners, and based on those adds some extra levels of refinement to make sure those features are also captured correctly. So this is simply the definition of the mesh that we created. Now let's have a look at the final result. This would be one of the meshes that we use. So let me, for example, show you how it would look like when we added some extra refinement. So this is one of the vents. As you can see, when we get close to this vent, the size of the cells are smaller than what normally we have in our domain. So this guarantees the quality of the solution to not diminish when we get close to this area. Same applies here to this vent. As you can see, we imposed a 3rd level refinement for both of them. Therefore, they are 1 level finer than what we have in the rest of the domain. Same applies to our second mesh that we use. It's really everything is the same. It simply is applied to a different geometry. So now I move on to the simulation designer. So as I said, we have 5 different cases. For 3 cases for smoke propagation and 2 cases for clearing of the smoke. Let's have a look at the first one. It's a transient analysis of smoke propagation. Since we only have smoke, I add only 1 passive species. It means that we have air, and on top of that we have 1 other element that is smoke. As I mentioned, I use K omega SST as the turbulence model, and our analysis is time dependent, transient here, because we are interested in seeing how the meshing front, how the smoke front evolves over time. Okay, so I use the first mesh that I created and I showed you earlier. Here in the model, I define two parameters that are kind of specifications of how the mass of how those tiny particles that are smoke move around inside inside the air. These two are really properties of the material. In this case, you will see we use air as the properties defined here. These two parameters kind of show how the smoke moves around inside air. So I added the material air. I think you're also familiar with our material library. You have several choices. In this case, this was air, so it's chosen from the library. We just assign it to the whole volume of the garage, and that would be it. So for the initial conditions, there's nothing special about the pressure, but we add a 0.1 meters per second in the direction of y as the initial condition. This is really just an initial condition. You can play around with it and see how it affects the results of the simulation. Same applies to K. Same applies to K and omega. We initialize them to a value that is relevant to our characteristic velocities that we have in our domain. Finally, we have to initialize the passive scalar. So here 0 means that initially there's no smoke in our domain. So the concentration is a value we choose here between 0 and 1. So 0 means 100% air, and 1 kind of means 100% smoke. Or maybe it maps to some level of smoke concentration. So when we have 0 here, it means that at time 0, before the start of the simulation, there's no smoke inside the garage. Then I move forward to set up the boundary conditions. We have an inlet of the smoke. This was that electronic equipment that is supposed to generate smoke. As you see, we have to specify some velocity. It means that the smoke enters our domain, the garage, with this velocity, and we also have to assign a value for the passive scalar. It's basically the concentration of the smoke. So this one says that from this boundary I have smoke, therefore passive scalar equal to 1, being injected into our domain with this velocity 0.35. This is what this velocity inlet condition is saying. Same here, it's just a different phase, but when we put these two together, this is the phases that inject smoke into our domain. We have an outlet. If you want to see which one it is, I'll just show it here. You can see this one, the far end vent is the outlet. In this simulation, we have the walls. We just use the predefined wall boundary condition with no slip, nothing difficult here. And we have an inlet here. This is the duct that is supposed to put some clean air inside the domain. Therefore, the passive scalar value is 0 here. Yeah, and this is it. The rest of the setup is the same as I said. Again, this and that are just injecting smoke into our domain simply because these faces, so these two at the bottom and these two at the top, because they have different orientations, we created different boundary conditions for them to assign the appropriate value for the velocity in the correct direction. But as you see, for all of them, the value of the passive scalar is 1. It means that it puts smoke inside the domain. There's nothing to be defined here. The setup is complete. The default numerical schemes are good. You don't need to change anything here. For this specific case, we have created the values in a way that you normally, if you're not dealing with certain features of the geometry or certain velocities, you don't need to do much here. The simulation control here, as always, we define based on the size of our domain and the duration of the simulation, how many cores we want to have. We define a maximum runtime to make sure the number of core hours that are being used are not exceeding from a certain value, and the rest is routine, as you normally do in the simulations on our platform. And here is the run. So let me see. Let's have a look at the final case. Here, as you can see, we have, it took about 660 minutes to have a final the final results. Here are the convergence plots. As you see, for some of them they go down because of the mixing. They start to have smaller and smaller gradients all over the domain. But since we are dealing with injection of some heat, of some concentration of mass inside the domain, not all of the convergence plots behave the same, and this is okay. So this was for a transient simulation of propagation of heat, of smoke inside the domain. It's the same for other cases. I will quickly show maybe one of the clearing cases. Everything is really the same. The only difference is here we initially want to have a non-zero value for our passive scalar to initialize the domain with a non-zero value, which means initially the domain is filled with a concentration of smoke. The rest is essentially the same. We have outlets, we have walls, we have inlets, and what we're going to do later is to rearrange this to see how the concentrations change. So with this, I would like to now go back to my slides and maybe discuss some of the results now. Okay. So first, let's start with scenario 1, smoke propagation, and with the case 1. So to just refresh your mind, the case 1 was we have a source that generated smoke and injected it inside our domain. This is the one that you can see here with smoke inlet on the left. And we have a transient simulation, so we want to see how the concentration and distribution of smoke changes over time. So on the first image here on the left, we are looking at the domain after about 1,200 seconds. So after this, we see this left part of the garage already has a concentration of smoke maybe around 0.5. But the interesting part is that the air inlet went, the one that we have here in the middle, kind of have created a kind of a cushion, maybe a curtain that restricts the movement of the smoke at this part of the garage. So if you compare this part with the other part that does not have the inlet, we see that here there's kind of a clear separation between the smoke and the clean air, while at the other part we have somehow a mixing. So this is after 1,200 seconds. Let's move forward to 2,500 seconds. So twice the time. As we see, as the time goes forward, the mixing enhances. So even though we still have a clear difference between the concentration of smoke in these two sides of our garage, but in both of them we have a visible mixing of clean air and smoke. And finally, after 4,800 seconds, which would be an hour, 15 minutes, we clearly see that in most parts of our domain, we have a rather high concentration of smoke. Maybe at some corners we still have clean air, but essentially all of our domain is now having a rather high concentration of smoke. So this is an interesting analysis because it shows us how long it takes for the smoke to move to all parts of the domain. It kind of gives an idea to the designers how much time you have to evacuate the garage, and while doing that, which are the passages that you can use to remove people and cars from the garage. So this is why this kind of transient analysis is helpful. Okay. So I move forward now and go to another case, still the case of smoke propagation, but I'm going to compare two cases. So one of them, again, we have smoke being injected inside our domain. I have the air inlet. This is the case we saw. I have the air outlet. But the difference is that here I'm going to have a steady state analysis and kind of measure some average values at the end. So when my simulation converges, I will have this distribution of air, as you can see here, and I'm going to see what is the average distribution of smoke inside the domain. So as you see, only at this tiny part, maybe less than 1/4 of our overall space in the garage, we have a concentration from 0.2 to 0.5, and that's it. So for the rest of the domain, we have very high concentrations, which means that virtually we have 1, which is the highest concentration that we can have. So this one shows that if we do a steady state analysis, if we wait long enough for that setup, this is going to be the final distribution of smoke inside the domain. As you can see here at the bottom, the average smoke ratio in the domain is going to be a little over 0.7. So this is the range of 0 to 1, 0 being air, 1 being smoke. So now let's look at a different case. We simply want to do a rearrange. Instead of having one inlet in the middle and one outlet at the far end, we're going to have 2 outlets in the middle and 1 inlet at the far end. So this is the case that I call the active management. So normally we don't need to have this, but in case of an emergency, if something happens, we want to change the way our system functions. And this is that case. We change this air inlet to be an outlet. We activate the other one on the other side to also be an outlet. And we change the functionality of that outlet to be an inlet. So here you can see at this steady state, when everything settles down, we have a clear distinction between the far end of our garage compared to the part that is closer to the source of the smoke. So here a very low concentration of smoke, virtually 0, so clean air, and here I have very high concentration because it is close to the source of the smoke. In this case, if we evaluate the average value of smoke concentration, we end up with something like 0.4. So 2 very important factors. First, the distribution. In this enhanced case, we have a distribution that is that completely gives a maybe more than maybe close to half of the area of the domain to have clean air. So this would be the place to have people and to remove people from the garage from. So this would be one, and second is the overall average concentration of the smoke, which is 0.4 compared to 0.7. So this is one of the cases how you can see such a design decision could be made very easily with simulation. What you need to do to have these 2 cases is to simply run 2 simulations, both steady state. We don't need to change the mesh. We only need to change the boundary conditions. In one case, have 1 inlet for air, 1 outlet for air, and 1 inlet for smoke. In the second case, which was the case in the right, we have 2 outlets and 2 inlets. We simply rearrange them. That's it. So you need to do a second setup, run them, compare the cases, and this already gives you a very clear idea of how to manage your system in case of emergency. Now let's move forward to the second scenario. We had smoke clearance. You want to see how this one works. So in case 1, we initially, as I said, we fill the domain with a concentration of 0.5 of smoke, and we run the case to see how the smoke is being removed from the domain. This is after 4,500 seconds. As you see, we have maybe a mix of both of the air and smoke. So at corners, since the mixing is very low, we still have higher concentrations of smoke. But at areas that we have a good airflow, we have a flow maybe from inlets and outlets, we have very low concentrations of smoke, virtually 0. The average concentration of smoke here is 0.1. Now let's change the scenario and see what happens. So what I do in the second case is to simply change the places of outlets and inlets with each other. So the two inlets in the case on the right become outlets, and the two outlets become inlets, and that's it. So again, no change in the mesh, no change in the geometry, we just change the boundary conditions. In this case, as you can see, the average domain, the average value of smoke concentration in the domain is lower. It's not much lower than what we had before, but the overall quality is more homogeneous than what we had. So in that case, we had areas which still had the maximum concentration of smoke and areas which had the normal healthy levels of smoke. In this case, this is distributed all over the domain, which means that we can guarantee a minimum quality of air all over our garage. This is interesting in cases like a normal garage where we never have a case, in a normal case, we don't have a case of fire, but we generally have cars that on a constant rate generate smoke. So it means that we want to be sure that at all times the quality of the air inside the garage satisfies some minimums. Okay, so these were the cases that I wanted to talk about. Two cases, propagation of smoke and clearance of smoke. We showed how tiny changes in this simulation could give clear indications which setup is better, which setup is fitting to our requirements without too much of investment, both in terms of computational cost or manufacturing or anything like that. So I hope our examples managed to show this to you. Now let's move forward to the assignment. We have prepared a case kind of similar to what we went over. We have smoke propagation in the parking lot. I would like to use a steady state passive scalar transport. The CAD model is provided inside the project. I will show you how to get the project. And this would be the specifics of this case. Let me show you first how to get the project, and then we move forward with the rest of the webinar. So if you come here and then go to the forum, you can here in the categories simply switch to SimScale webinars. Here we have the list of the webinars we have. At the bottom we have air conditioning and ventilation webinar. In here you can see we have both for session 1 and session 2 we have entries. If you come here in the session 2, you see a very nice step-by-step tutorial on how to first get the project, which has already the CAD model inside, and then create the mesh. You see every step is specified nicely, and then later move on to prepare the simulation itself, run it, and of course in the same way as we did now, get the results, analyze them, see what kind of setup, what kind of maybe inlet velocities, what kind of size for inlet outlet is more effective in this certain question that we have in mind. So yeah, so go ahead to this page, import the project. I'm sure the instructions that are provided here are going to be very helpful to finish up the homework. So with that, we are at the end of this session of the webinar. I hope you found it useful. Now it's time for questions, so it would be interesting to have your questions. I will go over them, maybe try to bundle them together and answer them. Let me just bring this question widget out to see a list of the questions. Also, I forgot something to show you. We also have prepared a few nice videos to show how the simulation that we just did reacts, how the results look like. So let's have a look at this one while the questions are being generated. Here we have, maybe I'll have a larger case. Here we have the case of having a smoke inlet and seeing how over time the smoke concentration increases in parts of our domain, how it evolves from the inlet towards the outlet. Once again, So you will see again, since we had an air inlet here, this part kind of acted like a cushion, moved the smoke to the other part. From there it moved on towards the outlet. This is one of the cases. We have another one, again, same scenario. This time we have the contours of the concentration. So this is again the first case. You can clearly see this line of separation here at this part of the domain. It shows how having one inlet here very significantly changes the propagation of smoke in this part of the domain compared to the other part. We also have a case for the scenario of clearance. Let's have a look at that, and then we will go to the questions. So here is the case where we have two inlets on the front and back, and two outlets on the sides. So again, initially filled with smoke with a concentration of 0.5, and then as we go forward, we want to see how the smoke is cleared from the domain. Okay. So now let's move to the questions. Okay, I have a question. Please show some basics of the user interface. I hope what we covered here did it. And we are also recording all of these sessions. So in case you missed parts of it or you want to go over some parts, I would encourage you to, both in the forum page, we put the links, also in our YouTube channel. I'll encourage you to go ahead and review the content of this session. So let's see. I have a question. Do you have experience in the simulation of ventilation with jet fans? It would be nice to have some more specifics. What exactly, what kind of, maybe more details would be helpful. So to give a general answer, it really depends on the specifics you want to have. What kind of velocities are you dealing with? So we normally encourage, especially if you haven't done much in an area, is to start simple. Maybe start with the geometry, make sure you get everything right with the mesh, do a simulation. Once you gain some confidence, move towards adding more complex boundary conditions, more complex concepts. For example, we have certain boundary conditions like mass flow, we have fan boundary conditions. So these are more advanced concepts that still are completely relevant in these cases, but it would be a good idea to not start with them right away. And also ventilation in tunnels. Yes, I think we have a couple of cases that somehow are close to this case. So I would say 80–90% of the case, the setup of the case is similar to what we show here. If you also want to look at the temperature distribution and do some analysis on heating and cooling of those scenarios, I encourage you to first have a look at the first session of this webinar series. Also, we have 2 more sessions coming, so I think in there you will also find some very useful information. Okay, you have a question. I don't understand what K omega should be. Where can I find information? So in our documentation, we have provided some instructions how to create initial values, how to calculate the initial values for these cases. But to put it roughly, these values depend on the characteristic velocities, some velocities that are typical of your domain, also some length, the characteristic length of your domain, maybe some length that shows a typical length in your domain. So if you go to our documentation, we have actually provided some formula for you to calculate them. But to get this out of the way, we intend to hopefully in near future provide this in a more automatic way. So you don't have to deal with, you don't necessarily have to deal with providing values in this level, but you can simply give more generics on the physics of your case, and then we calculate these values ourselves. I think I have a question about importing the file into the simulation. I'm not sure if I get this correctly, but if you're referring to the CAD model for the case of the homework, we already have provided it inside. Generally, if you have your CAD somewhere else, if it's on your computer, you can upload it. If you use on other platforms, for example, Onshape, you can directly import it, as I showed, from their platform into SimScale. And we are looking to extend this functionality. So in future, it's going to be even easier to do this. I have a question. What is the advantage of rectangular box for meshing? Well, the rectangular box itself, we have two rectangular boxes. One of them is the base mesh. So that defines the basic size of the element of the cells that your mesh is going to have. So the advantage of having that box is to have an idea what the level 0 cell, what the size of the level 0 cell is going to be. And how our measure actually works is that it starts from that regular Cartesian rectangular mesh and then carves out the features of the geometry from that. So this would be about that part, that it gives you an idea of the minimum level of refinement. We had a second rectangular box which was about the refinement. So we had that because we want to add an extra level of refinement on some certain parts of the domain. These parts of the domain are defined with some volumes. It could be a sphere, it could be a cylinder, and in this case it was a rectangular box. So it simply is a way to define refinements. Okay, I have why does the concentration generate circular curves, light or red, in the high smoke region? So this is not about the concentration of the smoke itself. This is about how the motion of the air is. So if we do a incompressible single phase simulation of that case, you will see the formation of these recirculating areas already. So it's important to understand the difference between these two. The flow patterns that we see there are simply because of the arrangement of the inlets and outlets, the viscosity of the air, the velocities that we have, and all of that. So introducing the passive scalar inside our model does not change the flow pattern, but it shows how certain quantities move around into the domain. It could be the case of the propagation of the smoke, or it could be the case of clearing the smoke from the domain. Somebody asked, why are the past two results so different? I'm not sure which results you're referring to, but if it's the case of two inlets and two outlets in clearing the smoke, where we change the place of the smoke, that is actually the point. So we showed that by changing the place, the arrangement of the inlets and outlets, you can get completely different results without having to make drastic changes in your design. I hope that answers it, but if you have more specifics, it would be nice to mention it. Is it possible to show the scale for the geometry? This feature is going to come soon. Unfortunately, we don't have it, and we are aware that it would be much nicer and much more clear to be able to show that in the viewer. This feature is going to come soon. We have how about fire source? What I understand from this question is to have heat. So it depends. If you want to simply visualize the propagation of a scalar like even temperature without changing the properties of the domain, like changing the properties of the air, scalar transport already is the answer. If you want to have heat and also the subsequent change in the properties of the domain, what you have to do is to use, for example, depending on your case, either conjugate heat transfer or our other analysis type, buoyancy case, this natural heat convection. There you actually can have sources for heat and then see how the temperature evolves in the domain. I think you have another question about heat and about volumetric heat source. This is going to be added soon as well. So if you use those heat transfer USD, you have to actually have boundaries to define some sources of heat, but soon you can actually simply define some volume and define some sources in that volume. We have a question, is it a custom solver for propagation? It's basically the scalar transport solver from the foam. So we simply use it for different turbulence models, but it's nothing really different than what's in the open foam itself. So I have a question, does it mean if this smoke is created at another place, another inlet-outlet configuration would be better? Exactly. And as you can see, it's difficult to give an answer to this question without trying. So to put it, in perspective, this is a what-if situation. So let's say somebody gives you the design and says that this is the best design. For example, the one that I provided. But since we're talking about a large project, there might be other concerns, like for some reason we cannot place a vent somewhere, or we have to change the arrangement of our electronics. This is a what-if situation where we say that, okay, no problem. Let's put the smoke inlet somewhere else and see if the current configuration still is better or if you have to come up with a better configuration. Okay. I think I have covered all of the questions or the ones that were not duplicate. Good. So I hope you've enjoyed this webinar and I hope it has been useful for you. I encourage you to, we will upload the, the video, the recording of this session soon. I encourage you to both do the homework and also come back to this video in case something was missing. And also, I really welcome all of the discussions we're going to have in the forum and look forward to it. Have a nice day and goodbye.